Thank you very much, Professor Jan Rack, in the first place, for the invitation and for organizing this conference. It's a great pleasure for me to be here. I wish to thank as well the organizing committee and Science 21 for the support for my participation in this conference. I'm very happy indeed, especially to be in Prague, where Kepler did meet Tycho Brahe, and that changed the history of astronomy, history of physics, and so on. What I will be talking today, it will be about Weber's electrodynamics. It's a subject I have been working on for 30 years now. Normally, in the textbooks, we learn about the four Maxwell's equations based on electric field and magnetic field, and also about Lorentz force law, QE plus QV cross B, also based on electric and magnetic fields. That's the standard theory. But what I will be presenting is a completely different electrodynamics, which is not based on fields. But keep in mind this Lorentz force and this velocity. In the textbooks, normally they don't discuss this velocity, but according to Einstein, it should be the velocity of the charge relative to the observer. I never was happy with that. That didn't agree with my physical intuition. So I began to looking for something different. And then I found Weber, which I will discuss here with you. So Weber was a German physicist. He worked in Göttingen University with Gauss. He was an experimentalist, and he was a contemporary of Maxwell. He was born before Maxwell and died after Maxwell. And Maxwell knew a lot about Weber. He quoted many times Weber in the treatise, in Maxwell's main book. And Weber also quoted Maxwell a few times, 5 times. But Maxwell knew a lot about Weber. So Weber and Gauss, they did build the first working telegraph, 1833, utilizing Faraday's law of induction, just 2 years after Faraday found his law. So Weber, just like Maxwell, he wanted to unify the laws of electrodynamics, but he did begin with a different, oops, it's not working. So maybe I change here. So at Weber's time, what did Weber knew at that time? He knew Coulomb's law, which is similar to Newton's law of gravitation. He knew Ampere's law, which describes the force between two current elements, which is similar to Newton's law of gravitation, I1, I2 over R squared, but depends on 3 angles. Angles between the two current elements and the straight line connecting them. And Weber knew as well Faraday's law of induction. The electromotive force is proportional to the time variation of current. So Weber wanted to unify these 3 laws, just like Maxwell, but not with field concepts. Weber was more like a Newtonian guy. He wanted to utilize force concepts. So Weber's idea was very simple. Let's suppose that current is charge in motion. So in Ampere's law, we should have V1 times V2, the product of 2 velocities. But we don't have that in Coulomb's law. So Weber said we should generalize Coulomb's law, introducing a term with V1, V2, so that we could deduce Ampere's law from a generalized Coulomb's law. And if current is proportional to velocity, di by dt should be acceleration. So according to Weber, he interprets Faraday's law of induction saying the following: when we change the current in the primary circuit, we induces a current in the secondary circuit. So if current is charging motion, changing the intensity of the current should be acceleration. So that microscopically, if you accelerate a charge in the primary circuit, there will be a force in the secondary circuit which depends on this acceleration. So he did need to introduce a component with acceleration in order to deduce Faraday's law of induction from a generalized Coulomb's law. That was his main idea. So this is Weber's force. So it is Coulomb's force, Q1, Q2 over R square, a term which depends on velocity square in order to deduce Ampere's force between current elements, and there is a term which depends on relative acceleration in order to deduce Faraday's law of induction. And there is a constant here, C. At that time, no one knew the value of this constant C. It was only 10 years later that Weber measure this constant. In principle, it has no connections with light. Weber just measured the force between two electrified spheres with Coulomb's torsion balance. Then he did discharge one of the spheres and measured the deflection in a magnetic compass. And then he knew the amount of current. And from these two force measurements, he did obtain the value of this constant, which just turned out to be the same as light velocity, showing a connection between electrodynamics and optics before Maxwell. That came from his experiment. So the whole of Weber's electrodynamics is in this slide. The whole, it's a single equation, scalar equation, no partial derivatives, very simple equation. The whole Weber's electrodynamics is here, okay? I will now show some consequences which Weber deduced from his force law. What are the main properties of Weber's force law? In the static case, when there is no velocity and no acceleration, we return to the laws of Coulomb and Gauss, the first of Maxwell's equations. It follows action and reaction, so there is conservation of linear momentum for a system of interacting particles. It also is a force along the straight line connecting the particles. So only from these, we deduce conservation of angular momentum. And Weber showed that his force law could be deduced from a velocity-dependent potential energy. This was the first example in physics of a potential energy which depends not only on distance, but also on velocity. So this means that the kinetic plus potential energy is also conserved with Weber's electrodynamics. So conservation of energy is also there. So the basic conservation laws, they are present with Weber's electrodynamics. The Faraday's law of induction can be deduced from Weber's law. I won't show it here. Those of you who wish, just give a look at Maxwell's treatise. It is 2 volumes. The last chapter of volume 2 is devoted to Weber's electrodynamics. In 10 pages, Maxwell shows that you deduce Faraday's law from Weber. You deduce Ampere's circuital law from Weber. What Maxwell took two books to prove with his theory, he shows with 10 pages with Weber, very simply. So Ampere's circuital law is also there with Weber. But what made me, André, to work with Weber's law, it was another property, which is that it is what I call relational. Weber's force depends only on the distance between the interacting charges, on the velocity between the charges, acceleration between the charges. The observer does not appear, does not matter. You see, that is different from Lorentz force law, as I said here. According to Einstein, that velocity in QV cross B is velocity of the charge relative to the observer. That's very strange to me. For this reason, when I found this property in Weber's law, I said that complies with my philosophy, with my intuition. So I decided to work with Weber's law. I found it in the book on the history of electrodynamics, because we don't learn any longer about Weber in the textbooks. It simply is not there. But when I found it in the history of science textbook, I said, that's what I was looking for a long time. So let us see what we can get with this force. So those of you who wish to see more details, 25 years ago, we did publish a book on Weber's electrodynamics. Nowadays, it is available by Springer. So I won't go into many details here. I will just show a few more examples. So, when we begin with Weber, we deduce Ampere's force between two current elements. So in the history, it was the opposite. Weber knew Ampere and deduced his force law, okay? In the textbooks nowadays, this equation does not appear. In the textbooks nowadays, we learn only this equation here, IDL cross B. This is a force law obtained by a mathematician, Grassmann, utilizing the magnetic field of Biot and Savart. So there are two cross products here. When we open that, we end up with this equation here, which appears in our textbooks. So that's the force between two current elements. So this is Grassmann-Biot-Savart that we learn in the textbook. This one is not in our textbook, but this was the one which Ampere himself introduced. So they are similar, I1, I2 over R square, I1, I2 over R square. So the first term is similar, but there is a 2 here which is not here. So it's not exactly the same. But especially the last component is completely different. Weber's last component is also a central force, points along the direction connecting the two current elements. The last component of Grassmann is not a central force. So they are very different. How could we forget about Ampere and keep only Grassmann? Let me show you. Suppose that we have two current elements like 1 and 2 here, which are orthogonal to one another. According to Ampere, they will not exert a force on one another. The force of 2 on 1 and 1 on 2 is 0, according to Ampere. But according to our textbooks, the element 2 will exert an upward force on element 1. But element 1 will not react on element 2. So the law that we learn in the textbook does not comply with action and reaction. And suppose now that we have two elements which are aligned with one another. According to Ampere, they should repel one another. according to our textbooks, they don't exert any force on one another. When Ampere discovered that they should repel one another, Ampere himself was very surprised with this result. And he devised an experiment, which I will show here in a minute, to test this strange effect. And he found it in his experiments. But, so, you can see the two laws, they are very different. So how could we forget about Ampere? Because, although they are very different, they have a very unusual property. When we integrate the force of a closed circuit acting on an element of another circuit, both agree with one another. When we integrate, Ampere is equal Grassmann, which is this expression which we also find in the textbooks. So if we have two or more closed circuits, we cannot distinguish Ampere from Grassmann. So if we have only closed circuits, we can choose which one we want to work. So for this reason, we can work with Grassmann as in the textbooks, as usually we have only closed systems. But maybe that's not always the case. But they only agree for closed circuits, not for current elements. There are many experiments try to distinguish these two force laws, even nowadays. This was an experiment performed originally by Ampere himself. He wanted to see the repulsion between this element and this one here, or the repulsion between Fe and Gf, okay? And so Ampere devised this experiment, which is called Ampere's bridge experiment. We have mercury here, and when there is current, it moves away from the source. Okay, this was an experiment devised by Ampere to show the existence of these longitudinal forces. There are other experiments, exploding wire and so on, showing the existence of these longitudinal forces. I worked for 1 year in Boston, almost 30 years ago, with a guy called Peter Grano, who made this kind of experiments. I worked with him there and so on. But I won't go into the details here. So Maxwell himself, he knew not only Ampere's force, but he knew Grassmann's force as well. And in his treatise, Maxwell made the following statement, comparing Ampere, 1826, Grassmann, and two other expressions which Maxwell himself created. Then Maxwell made the following statement. Of these four different assumptions, that of Ampere is undoubtedly the best, since it is the only one which makes the force on the two elements not only equal and opposite, but along the straight line which joins them. That was Maxwell. He didn't like Grassmann. He did prefer Ampere. He said something else, which I will show here in the next article, paragraph. Maxwell, the experimental investigation by which Ampere established the laws of the mechanical action between electric currents is one of the most brilliant achievements in science. The whole theory and experiment seems as if it had leaped, full grown and full armed from the brain of the Newton of electricity. And it is perfect in form and unassailable in accuracy. And it is summed up in a formula from which all the phenomena may be deduced, and which must always remain the most important formula of electrodynamics. that is amperes force between current elements. Maxwell said it should be the most important, always. But it does not appear in any textbook nowadays. It is gone. Completely gone. Also, Maxwell himself said explicitly that should remain the most important formula of electrodynamics. Why it did disappear? Because nowadays we utilize not only Maxwell's equations, but relativity, Einstein. And relativity is based not only on Maxwell's equation, but on Lorentz force law. And with Lorentz force, we deduce only Grassmann. We cannot deduce Ampere's force with Lorentz. With Weber, on the other hand, we deduce Ampere's force between current elements, not Grassmann. So they removed Ampere. Otherwise, the students would make questions to the teachers, and it would be problematic for them to answer. I won't go into the details here. For those of you who wish, we have two books. One comparing Grassmann and Ampere, and also comparing different formulas for self-induction. There is one by Franz Neumann, one by Maxwell himself, another by Weber. But I call your attention, especially to this book here, in which it's like a 500-page book, and we made a complete translation of Ampere's book from French to English. Ampere had never been translated. There was only a partial translation by Tricker, 1965. Now we made a complete and commented translation of Ampere's masterpiece from French to English. You can download it from our homepage, okay? I won't go into more details here. I will move ahead. Let me show you another fascinating property of Weber's electrodynamics. In 1857, Kirchhoff, he was just like a student of Weber and so on, and Weber, they were the first to deduce the propagation of signals along a telegraph cable. In particular, Weber and Kirchhoff, they did, this is Ohm's law, current proportional to the electric field. But they did generalized Ohm's law by taking into account not only the usual electric field, but self-induction of the wire. And this is the law of the conservation of charges, which Maxwell utilized with his displacement current and so on. And here we have like a wire, and a conductor, and we make a perturbation, like we close or open a switch and so on. So there will be a signal propagating along the wire. And then that is before Maxwell, 1857. Then they deduced, based on Weber's electrodynamics, the following equation, which they published in the Annales in der Physik, which is the telegraphy equation. This is the wave equation when this is equal to 0, but if there is resistance in the wire, the signal, the intensity will decrease exponentially. So they were the first to deduce the correct equation of propagation of signals, which is the telegraphy equation. In particular, if the wire has no resistance, we obtain the wave equation. But you see, this was published by Kirchhoff before Maxwell, utilizing Weber's action at a distance law. No displacement current, no fields, nothing, just Weber's action at a distance law. Nowadays, in the textbooks, we call this Ampere's law, but Ampere never wrote such an equation. Ampere never worked with a magnetic field. In fact, Ampere fought against Ørsted, against Faraday, that there was something circulating along a wire. Ampere fought against these ideas. The first one to deduce this equation was Maxwell himself. Then Maxwell corrected himself by introducing the displacement currents. We see that in the textbooks. But the textbooks, they don't mention the following. The constant C, which appear here, Maxwell borrowed from Weber's force law. Weber had introduced this constant, which is in the international system units, 1 over square root mu naught epsilon naught. Maxwell knew the numerical value of this equation, which Weber was the first to measure. Weber was an experimentalist, not a theoretician. And he found light velocity. And Maxwell knew the wave equation, which Weber and Kirchhoff had deduced. So when Maxwell introduced the displacement current, he knew the value of that constant, which was light, and he knew that it would be reasonable, possible, to deduce a wave equation with that, because Weber had already published that before Maxwell. But this information here is not in the textbooks, okay? It seems as if Maxwell, out of the blue, introduced the displacement current and then suddenly obtained the wave equation. That's not the way history was made, okay? Let me now go back to Weber. There is one, this is Lorentz force, this is Weber. They are very different, okay? Nothing at all similar to one another. But what I want to show, the main difference between the two, is that in Lorentz we have a component which depends on the velocity of the test particle. But there is no component here which depends on the acceleration of the test particle, A1. With Weber, on the other hand, we have A1 here, A1 and A2. So it depends on the acceleration of both interacting charges. So I will now discuss this main difference between Weber and Lorentz, okay? So there is no component here which depends on acceleration, but there is one here. Let me just show a very important distinction between Weber and Lorentz. Suppose, for instance, that I charge, this is plastic, I charge it in my hair, so it is electrified. So there is these walls of this room here. I can charge the walls, okay? And then I charge it here and accelerate it with my hand. And I ask, will the walls of this room exert a force on this accelerated charge? If the walls, if they build a spherical shell, so there is inside a constant potential and no electric field inside due to the shell. So the shell will not exert any force on the accelerated charge inside. Okay? This is according to Lorentz. But according to Weber, there will be a force. If I charge it here and try to accelerate it, so according to Weber, the electrified walls will exert a force on the test particle, which depends on the amount of charge which is in the shell, depends on the radius of the shell, and depends on the relative acceleration between the test particle and the shell. So the two expressions, they are very different from one another in this example. They are not always similar, okay? And what happens if we spin the shell? Now suppose that we spin the shell and we have a particle inside which has a velocity and an acceleration. When we spin the shell, according to Lorentz, the electric field inside will be 0, so there is no force here. But in this case, there is a uniform magnetic field inside the spinning shell, just like an infinite solenoid. The magnetic field is homogeneous here inside. In the outside, it is a dipole magnetic field, but inside it is homogeneous magnetic field. So there should be this force QV cross B. When we perform the calculations with Weber, we obtain 3 components. The first one is the one in the previous slide when there is no acceleration of the shell, which is not here. But we have also a centrifugal and a Coriolis force, according to Weber. And this Coriolis force is exactly the same as QV cross B, because it 2 cancels with this 12, 1/6. So the magnetic force is essentially a Coriolis type of force. But according to Weber, there is also a centrifugal electric force. So we hope in the future someone will test this prediction experimentally. Maybe Professor Ian Hack or someone else, who knows. Let me now show you another fascinating property of Weber's electrodynamics that is gone from the textbooks. No one else talks about it nowadays. So suppose we have just 2 interacting particles, okay? Q1 and Q2. So according to force equals ma, Newton's second law of motion. But so if we have 2 particles interacting with one another, if the velocity is small compared with light velocity, we can cancel this middle term, okay? But according to Weber's law, this last component, it has one component which depends on the acceleration of the test charge, A1. Charge 1 is the test particle, okay? So we can call it like a Weberian mass times A1. What is this Weberian mass? Q1, Q2, 4 pi epsilon naught, 1/c square, and this r cancels with this r square, so it is 1/r here. So, okay? So this is just this last component here. It has a proportionality constant with the unit of kilogram mass, and depends on the acceleration of the test particle. So we can move this term to the right-hand side. So we will end up with Coulomb's law equals an effective mass times acceleration. What is this effective mass? It is the usual mass of the particle minus the Weberian mass. Okay? This is just 2 charges interacting according to Weber's law. And this Weberian mass here is Q1, Q2 over R. So it can be positive when we have 2 charges of the same sign, or it can be negative if the charges have opposite signs. And the order of magnitude, if R is great, so we can neglect that. But if the distance is very small, this Weberian mass here can be much larger than the usual mass of the particle. Okay? So this term can dominate this one. And we can ask, when will be the 2 masses equal to one another? So we make this equals to this, then you find what Weber called a critical distance. Okay? this calculation was made by Weber himself. Two-body problem interacting with his force law. You see, so if the two charges have the same sign, like two positrons, this Weberian mass is positive, M1 minus Weberian mass can become negative if the distance is very small. So the particle can behave as if it had a negative effective inertial mass. This is just fascinating. So what is the main consequence which Weber himself deduced from these calculations? Weber proposed a nuclear model of the atom in which the negative particles would describe ellipses around the nuclei, but the nucleus would have two or more positive charges which would attract one another. Why would they attract one another? Because they behave as if they did have negative inertial mass. So the force is in this direction, but as they have negative inertial mass, they attract one another. That is just fascinating. So that was Weber's model of the atom. Not only that, with Weber's law, it's not an exact ellipsis, it precesses. There is a precession of the perihelion with Weber's two-body problem. However, this number here, it was not obtained by Weber himself, because he didn't know about the positron or about the electron. He just, in his mind, he said, we can have a model of the atom like that, but he couldn't give numbers to the size of this critical distance and so on. But he published this during his lifetime. So let me show you some remarkable properties of Weber's model of the atom. In the first place, it was a prediction by Weber, 1870-1808. It was made before the discovery of the electron, before Balmer spectral series, before Rutherford scattering experiments. Bohr's model, on the other hand, was invented in order to be compatible with these experimental findings. Weber was a real prediction, but no textbook talks about this. The textbooks only mention the plum pudding model of Thomson, and then they go on to Bohr, okay? But before Thomson, before Bohr, came Weber. Moreover, Weber presented a formula for his critical distance, below which two charges of the same sign would attract one another. But he could not calculate the value because the electrons and the positrons were unknown in his times. But when we nowadays put the numbers, let me just show you again the formula. If we just put in this formula here, the charge of two positrons and the mass of a positron, now we can give numbers. So what will be the critical distance when two positrons, instead of repelling one another, will attract one another? Now we can give numbers. When we do and give numbers, we find 10 to minus 15 meters, which is the known size of the nuclei. It cannot be a coincidence, I guess. To me, this is the correct explanation, not only of the constitution of the atoms, but a justification of their size. Why they have this size, okay? So Weber's model gives a justification of the known size of the nuclei. It is just fascinating from my point of view. And the most important last property, in modern physics, we need to postulate nuclear force to prevent the explosion of the nuclei, because they should explode due to Coulomb's repulsion. But with Weber, you explain the stability of the nuclei by itself because they behave with negative inertial mass. So you already have a unification of electrodynamics with nuclear forces before they were separated. To me, that is just fascinating. I believe this is the correct explanation of the nuclei, why the atoms are stable. And this model has been forgotten in the last 150 years. So those of you, please, go ahead and begin to work with that. All the properties are here to be developed, okay? If you get motivated, just go ahead. Everything is here to be developed. It has been stopped 150 years ago. Those of you who want to see more details, we have a book with two German colleagues of mine about Weber's planetary model of the atom, which we published 8 years ago. Okay, you can give a look. So let me now just tell you my own next project. I want to publish the English translation of Weber's main works on electrodynamics, just as I did with Ampere, translating from French to English. Weber's work, most of them have never been translated to any language, but especially to English. Only a few of them, very few of them have been translated. And nowadays, that is one of the main reasons why it has been forgotten. So I have been involved in this project for some time, and I am looking for volunteers to help translate any of Weber's papers. 20 years ago, I did spend 2 years in Germany. And then, at that time, I read essentially all of Weber's papers. They have been collected in 6 very large volumes, and I read essentially all of them, but and I can tell you that there are many jewels, many beautiful results in these works of Weber, which are completely unknown nowadays. So ideally, this volunteer should be a German-speaking physicist. So if there is someone here in the audience, or if you know someone at home who would like to help in this project, please ask this person to get in touch with me. In my homepage, you can find my email there. So please, I would like to have help, because some of Weber's papers, they are just like Ampere's book, 200 pages. So it's not a simple task. But so that's my next project. So if I would like help, so if you know someone, please ask this person to get in touch with me. So in conclusion, Weber's electrodynamics is extremely powerful. It is the electrodynamics in which I believe, in which I have been working for 30 years. And in the last few years, there has been a renewed interest in Weber's electrodynamics due to novel experiments and new theoretical developments. So if you have questions, please. Thank you.